We learned when we talked about momentum in Physics 141 that momentum, classically, is a product of the mass of an object times the object's velocity. So the larger the mass of the object, or the larger the velocity, the more momentum that object had. And then we use that concept of momentum to talk about collisions and how momentum is conserved in collisions where there are no external forces working on the object. So the initial momentum of a system is equal to the final momentum of the system after a collision or explosion occurs. But classically, momentum then, the object has to have a velocity and a mass. What about light? Light does not have mass. So classically, light should not have momentum. Well, it turns out that's not the case. Light does have momentum. And this was shown in a series of experiments by Compton, who won the Nobel Prize for this. Your book explains the experiment. By having light bounce off of charged particles, Compton proved that light indeed carries momentum. The equation for momentum when you're talking about light, the momentum of a photon is equal to Planck's constant. Again, we're going to be seeing Planck's constant a lot in this part of the modern physics part of the lectures, over the wavelength of light. So again, Planck's constant, 6.626 times 10 to the minus 34 joule seconds. Wavelength here is the wavelength of a photon, so wherever the photon wavelength is. So the smaller the wavelength of the photon, the higher the momentum. And the experiment that Compton looked at was taking a photon of a certain wavelength, lambda, and crashing it into a stationary, or approximately stationary electron. That electron flies off with some kinetic energy and some momentum. That is a particle with mass. It flies off with some velocity, so it carries with it some momentum. It might be the relativistic version of momentum we learned about earlier in section 2.5, or lesson 2.5. But it is momentum. Where does that momentum come from? It comes from the momentum of the photon. So the photon ends up leaving with a larger wavelength, which means it's leaving with a smaller momentum. So the changing kinetic energy, and this is a collision where momentum is conserved and kinetic energy is conserved, or energy is conserved. So the kinetic energy of the electron as it flies off is equal to the initial energy of the photon coming in minus the final energy of the photon. The photon loses energy during this collision. How much energy? Well, it depends on, again, the energy of a photon is Planck's constant times the frequency of the photon. So the initial minus the final energy of the photon is equal to the changing kinetic energy of the electron. This is called Compton scattering. There's also inverse Compton scattering, where a high energy electron can hit a photon and give that photon energy. And that energy comes from the kinetic energy of the electron. We see this in very high energy jets around black holes. So there's Compton scattering when a photon transfers energy to an electron, and inverse Compton scattering when a high energy electron transfers some of its energy to a photon. So this equation for modern physics, right, photon energy, if we look at relativistic photon momentum, your book talks about the relativistic energy equation for a particle. If you recall, it was E squared is equal to mc squared quantity squared plus pc quantity squared. But for a particle with no mass, this term goes to 0. So E squared is equal to pc quantity squared. Take the square root of both sides. The energy of a particle is equal to the momentum times the speed of light. Solving this for momentum, momentum is equal to the energy of the particle over the speed of light. Energy of a photon is hc over lambda divided by c. The c's cancel. Momentum of a photon is h over lambda, which is what we have here. So the relativistic momentum of a photon is the same as the momentum of a photon. So photons carry momentum. So in these collisions, we can calculate the momentum coming in, the momentum leaving, in the x and y axes if we have to, if it's two-dimensional collision, how much momentum is transferred to the electron, figure out the electron's velocity, figure out the change in the electron's energy. So photons have momentum. Classically, this equation works just fine in the macroscopic world. When we start talking about the microscopic world or the atomic world, really, we have to worry about the momentum of particles. And this equation becomes important in our next section when we talk about wave-particle duality.